here's a theorem. I'm condensing it a little bit. If G composed with F makes sense, meaning that the range of F is contained inside the domain of G, etc. If F is continuous at X, if G is continuous at F of X, then G composed with F is continuous at X. I'm going to give an example to explain this, and I think kind of the weirdest part is that G has to be continuous at F of X, but hopefully my example will make sense. So in my example, I'm going to let G of X equal 1 if X is bigger than or equal to 0, and 0 if X is less than 0. And I'll let F of X, let's just make it equal to X minus 1. So notice, very briefly, the graph of G is just going to be this, which is continuous except at 0. And similarly, you all know the graph of F, but just to be completely sure, X minus 1 looks something like that. I'm going to compose these. And of course we can compose these pretty naturally. G composed with F of X equals G composed of F of X equals G of X minus 1, which equals, well, it equals 1 if X is bigger than X minus 1, if the input, right, G of X equals 1 if the input is bigger than or equal to 0. So G of X minus 1 equals 1 if the input is bigger than or equal to 0, and 0 if X minus 1 is less than 0. In other words, it equals 1 if X is bigger than 1, and 0 if X is less than 1. In other words, the graph of that is going to look like, basically we're just going to slide it over. So now it's continuous except at X equals 1. That's G composed with F. And this is just G, and that's just F. Well, let's see, pretty clearly, let's go through our checklist. I'm going to let C be equal to, say, 1. Definitely F is continuous at 1. Right, we can say the limit as X approaches 1 of F of X is going to be equal to 1, F of 1, because it's a polynomial. And that equals 0. So notice I have F is continuous at X. I suppose I should call this X. G is not going to be continuous, because what happens? F of 1 is equal to 0, and when I plug 0 into here, I get discontinuity. So F is continuous at 1, but F of 1 equals 0. G is not continuous at 0. So imagine for a second that all we knew were these two functions. What this theorem says is G composed with F, pretend like you don't know any of this over here. G composed of F continuous at 1? Well, F is continuous at 1, sure. But F of 1 equals 0. G is not continuous at F of 1, which is 0, because of this. So G composed of F will not be continuous at X equal to 1. So notice we can figure out whether G composed with F is continuous at X without ever computing G composed with F. Now, I did compute G composed with F here to show you what I'm about to show you now. Right? It's not continuous at X equals 1. Well, great, that's what our graph showed, because G composed with F equals 1 if X is bigger than or equal to 1, and 0 if X is less than 1. The point of this theorem is you don't actually need to do all this stuff to figure out if G composed with F is continuous at a certain point. All you need to do is see if is F continuous at X? Is G continuous at F of X? And then you don't need to go through this whole thing of, oh, X minus 1 bigger than 0, blah, blah, blah. You can just save yourself a lot of work. That's the point of this theorem.